Although in this lecture I will focus about the numerical problems in a 2D descriptional sense. That means that we only describe our moments clockwise and counterclockwise. I want to go ahead and define the proper 3D definition of moments, since we're talking about moments right now and we don't have to come back to this in our following lecture. So let's go ahead and, while it's so much fun, define 3D moments. And therefore I have these pictures here created and I'm gonna add something to them. So let's say I have, for example, here an x-axis, and then the wrench here is actually the y-axis. And therefore you can say that this f here is actually parallel to the x-axis, so that's fx, whereas d is parallel to the y-axis. So fx is parallel to x-axis, whereas dy is parallel to the y-axis. And together they create a tendency for rotation about point O. So these force and lever arm create a rotation about this point. And of course you can already see here we're pushing in this direction, so we're trying to loosen the bolt actually. And now for the 3D description, right, we rotate from positive x to positive y. So if we rotate in that direction, then we actually end up with a positive z direction. So in this case, m about point O is equal to fx times dy. But now the important point that I want to point out to you, it's not enough to just say about point O. It's also important to state about which axis this rotation happens. And you already understand this from our previous discussion, that if I rotate from positive x to positive y, I'm moving in the positive z direction. So I better state here that it's actually mo about the z-axis. And that means that here on the top, we actually have to identify this as z-axis. Now let's take a look at the next picture, where I'm going to add this coordinate system again for us. So let me zoom in and add an x-axis, and then also add an y-axis, which is acting in this direction. And now I have a force that is actually parallel to the z direction, and I have a d that is still parallel in the y direction. Of course, nobody really sane in their mind would actually push on a wrench this way, right? So this here is parallel to the z-axis. Let me clarify this a little bit better by adding the z-axis that is going down here. That would be the negative z-axis. And so the fz and the dy are now in effect. But again, nobody would ever rotate a wrench like that unless you try to break something. But it is important for us to understand that there's still rotation created about this point. So now we have a force parallel to z-axis, and our dy is still a lever arm parallel to the y-axis. And together, these create a tendency to cause rotation about which axis now? That's the question, right? So let's look at that. So now I'm rotating this force here, Fz, to this point with lever arm dy. And what that really means is that I'm rotating from positive y to positive z, right? So imagine this. So I'm turning from positive y 2 positive z, and that means that I have actually rotation about the x-axis. So about the x-axis. And that means that up here I need to add my headline x-axis. And this is important to understand that now I have MO about the x-axis being equal to FZ times dy. And maybe you start to notice a commonality here if I zoom out again and would take a look at both of these pictures. So you see that I have x, y, z. X, Y, Z. So it always has to be three-dimensional because you rotate about the missing axis, if you will. And this is a rule you can pretty much remember and engrave in your brain because it's something you need to understand when it comes to 3D moments. But the general rule is that you always need all three subscripts. Otherwise, you cannot create a moment. And that takes us to our last concept here on the bottom of the page. Let's take a look at that now. I will add the coordinate system again. So here is my x-axis. And I have a y-axis. And so that means that I have an Fy here. So F is actually parallel to y-axis. And let's look at our D. Our D would be somewhere here, which is acting from there to there. So this would be D, and it would also be in the y direction. So dy would also be parallel to y-axis. And therefore, you really have no tendency to rotate. And I can explain this in two ways. One is probably what everybody is thinking right now, which is the y and y. I don't have two subscripts that are different from each other so that I could create the third one, which would make sense in the context of this entire page that we just created here. So this is the mathematical reason, if you will. That definitely applies. Therefore, you don't have a tendency to rotate. But physically speaking, it's actually more important to think of this as the point of interest. So the problem here is actually that the force passes through the point of interest. So Fy is passing through this point. The line of action of Fy passes through the point of interest. Let's write that down. That is very important. So line of action of Fy passes through our point of interest. And therefore, no moment, right? No moment. Because you cannot create a tendency to rotate, or like you can also think of it that it could not rotate. It doesn't matter if it's a tendency or actually created rotation. If you put a needle here, think of it as pinning a needle here, and then you pull with a string on that needle, you will not rotate that string about that needle. You will actually just pull on it. And therefore, you create no moment. It cannot be created. In other words, we need to say here rotation about no axis, or about no direction. And later on, of course, you will not always talk about XYZ direction. It will actually be randomly oriented. It will not be as beautiful as it is here or here or here. It will be random in space. But if you understand this concept of the direction, you will be a big step ahead because, as you know from anything in vector decomposition, you can always break it down into X, Y, and Z components. And if you understand this concept here, then you understand how the components create different moments. But for now, let's take away that we always have two dimensions that create the third one, or the rotation about the third one. And more importantly, that if our line of action of a force passes through the point of interest, then we will not create a rotation. Let me follow that up with one last thing here on the bottom. If, for example, I were to weld something to my wrench here, let's say I weld an extension to it here, and of course you have to imagine that the hand is gone there, it's welded to the system here now, and now I'm gonna add the force Fy, but I make it attack here, so Fy, then I actually would have a distance to the point of interest, and that distance would actually be this line here, or better indicated by this here, which then would be called dx because it's parallel to the x direction. And now this would create a moment about point O, although I'm using Fy, right? I just shifted Fy here because I extended my wrench by this thing that I welded to it. And therefore, I made sure that Fy does not pass through the point of interest anymore. And so what you have to take away from this is that it's actually always the force times the lever arm. As long as you do have a true lever arm to it, you will always create a moment. There's one more thing that we need to talk about. I will do that on the next page, but I want you to think about it right now with me. And that is what part of the force actually creates that moment, right? It's not just any force times any distance. There's actually something very important to take away from all of this here. It's kind of hidden behind it, but it is the fact that it's the force times what's often called the perpendicular distance. So what people often write is that m is equal to F times d perpendicular. And that is something that we get to explore a little bit further on the upcoming page.